Hello, students, and welcome to today's lecture where we are going to be going over the rate law. Okay, and this rate law is actually kind of like a way that we can go ahead and think about how concentration can affect uh, different reaction speeds. And we have a combination of different concentration effects that we're going to go ahead and watch out for. Okay, so first what we're going to go ahead and do is we're going to talk about real quickly what the rate law actually is and what it does. Okay, and this is essentially a way for us to go ahead and trace what kind of reaction that we have. Okay, and in it, we have a couple of terms that we're going to be concerned with. First, we're going to be concerned with the rate because this is, again, reaction rates. And the rate is going to be equal to K, which in this case, K is going to be our rate constant. And this is going to be a constant that's for the reaction, okay? And so this K value is for each different reaction. Each reaction will have its own K value, and it's something that we have to watch out for. And then it's going to be times the concentration of the reactant, okay? So whenever you see this bracket here, it means it's going to be times the concentration of the reactant, okay? And then the one that we're really most interested in is going to be this N value, okay? And this N value is going to be what we're going to be interested in finding out for a lot of different rate law factors. And it's going to tell us the order of a reaction or how reaction rate changes with concentration. All right. So essentially, this next slide is essentially talking just about K. And this is just a constant or the rate constant for a reaction, and it has to maintain a constant temperature. Units are dependent on order of the reactants, okay, so it depends on what reactants are in there. And we always have to use experimental data in order to discover what K is going to be, okay. And then even though we're going to have the term integrated rate law right here, we're actually not going to worry any real amount about the amount of math that we're going to have to do with this one, because I'm going to show you guys a real shortcut method for how to deal with this for data that we collect this way. Okay. And these are some of the information that we're always going to need in order to determine this. So in each reaction that we have, that's going to be where we're going to determine the rate law, you're going to be given a couple of things. You're going to be given concentration, and then you're going to be given the rate. Okay, so you're going to be given this term and this term, and then we're usually going to be solving for N, which is this term right here. Okay. And then we'll also be solving for K after we solve for N, because we're going to be able to solve for N by looking at it. And K, if we ever needed to solve it, is just going to be a plug and go type of situation. Okay. So what we have here is we have the kind of ugly mathematical terms for this one right here. And what I want us to take a look at here is, instead of looking at these mathematically, I want us to go ahead and think about the three different types of rate laws that we have as we go forward. Or I want us to go ahead and think about what's going to happen in particular to a reaction rate when they have a different order, okay? And the first one is going to be a zero order reaction, okay? And we're going to go ahead and take a look at the zero order reaction, which is this one right here, okay? And when we have a zero order reaction, what you'll notice is that as the reaction goes forward, that there is no slope at all, or there's no change in the slope or the reaction rate at all, okay? And what that means for us as a zero order reaction is that zero order reactions do not become affected by concentration. So that means that the reaction is going to happen at the same pace no matter what the concentration is. So concentration has no effect on a zeroth order reaction. Okay? And that's what we need to know here. And what I want you to see in particular here is that when we do graph a zeroth order reaction, what we'll notice is that we have a slope. And since we have a nice straight line slope, that means that we can figure out what our K value is, or the reaction rate constant, or the reaction rate constant for that reaction. All right. So that's essentially what's going on there, is that since we have a zeroth order reaction, we can figure out K, which is the rate constant, just by plotting it out and then using our essential algebraic form to figure out what that is. But I'm more interested in you guys being able to plot it and then see what it looks like. In fact, that's what our lab is going to end up being. Okay. The next type of reaction constant that we could have is going to be a first order reaction. Okay. And so this graph right here is showing a first order reaction where we have concentration here, and then we have time here. And what I want you to notice is that this one is a curved line here. Okay. So this is a curved line, and theoretically we could go ahead and break out the calculus and we could try and figure out, okay, what's the slope of the curve right at this particular point? But there's a better way and an easier way for us to do it, okay? What we can do if it's a first order reaction is that we can go ahead and graph our calculations, our concentrations in time, and instead of leaving it just as concentration, we can go ahead and do the natural log of the concentration. And what I want you to notice is that for a first order reaction, what will happen is that all of these terms right here end up making a new straight line, okay? And here, the K would end up equaling the slope of this line, all right? So for a zeroth order reaction, concentration versus time, it's a straight line, okay? For a first order reaction, we have to have the natural log of the concentration versus time, and that gives us a straight line. So that means that if you are given a set of data to analyze, all that you would have to do is graph it, okay? Go ahead and put it into the graphing calculator and see which one ends up giving you the straight line, okay? And again, with how we've been doing our data set for this, you know, we'd be able to go ahead and plot our straight line and then use our lining tool to go ahead and figure out what the actual K value would be, okay? So this is a first order reaction, which means that this one over here is going to be our second order reaction. Okay, and the second order reaction is going to be 1 over the concentration, and what will happen is that it'll give us a slope going upwards here, okay? So graphically, all three of these reactions look the same. Now, we're going to go ahead and think about these reactions in terms of our original equation right here, okay? Because the numbers that we discovered, 0, 1, 2, or 3, are going to be multiplied by this right here, okay? So if we have a zero order reaction, that means that this number here will be 0, and an exponent to the 0 means that whatever it's multiplied to is going to be turning into whatever it's the exponent of is going to turn into 1, which means that the rate is going to equal the rate constant, which, looking at our integrated rate law right here, the rate equals the rate constant. The rate doesn't change depending on concentration. Okay? If we think about this particular formula, if we have a 1 there, then the rate is going to be affected by the concentration by a power of 1. Okay? So let's think about that logically. Okay? That means that if half of our solution disappears, if we use up half of our reactants, that means that we would expect that the rate of reaction would slow down to 1/2. And that's actually what we would end up seeing. All right? So if we have a reaction rate and it's, consuming 100 particles per second, and then, we allow it to go forward to second 2. At second 2, it'll only consume 50 particles per second because now we have less reactants that we can use for it, okay? Now, if we go ahead and think about, the third one right here, or the second order reaction, we would expect that would consume particles twice as fast, okay? So that means that as the reaction goes forward, that it'll go twice as fast, which means that if we use up half of our reactants, we'll now be going at a quarter of a speed instead of half the speed as before, okay? And let's go ahead and get past here. All right. So here we have an example here where we can go ahead and take a look at some data here. All right. So here we have our concentration and we have the time. Okay. Now notice that as we go down and as we go down in terms of our concentration, and as we go with the time, that we see this direct relationship between our concentration and how much time. Half of it got used up in 100 seconds, okay? Or if you want to go ahead and take a look at this one in particular, we used up 0.05 moles per liter of our original compound in 100 seconds. The next 100 seconds, we only used up, from here to here, we only used half as what we used during the first 100 seconds. Okay, so we have a 1-to-1 relationship. Okay, and you could tell that because, as you go down by, as you go down by a unit, you're only losing half as much as you used before because your reaction rate has slowed down. Okay, so this is an example of a first order reaction and the type of data that we would expect to see in a first order reaction. Okay. And then if we wanted to go ahead and graph it out, we would have to go ahead and just do the natural log of the concentration, and our time would be the same. And then we would end up being able to graph it linearly like this right here. Okay. And I'm not really too concerned with us graphing and figuring it out from here. Okay. But I do want us to be able to see it here. And yeah, that's going to be it for us for right now. All right, let's see. Alrighty. So, let's see here. I'm trying to find, I wish I had a second one here that ended up looking good. You know what? I'm not having a good luck finding a good set of data for the second order reactions for right now. Little unprepared, but that's okay. That's okay. We're doing our best here. Okay. So realistically, what we'll end up doing for this is that I'm going to end up making essentially just a couple of graphs for us to look at, and we're going to be able to look at this both just like looking at a graph like this, and then for our big lab for this section, we're going to generate some data for this, and with that data, we're going to be able to essentially see if a reaction's a first order, second order, or third order. And that's all that we're really looking to do with this data right here. We don't actually have a requirement of discovering K for a reaction, but we will be wanting to figure out if a reaction is going to be a first order, second order, or third order based off of data things like this right here. Okay. And then, of course, because graphing is such an important part of this class, we're also going to want to go ahead and practice out with some graphing of this data. And like in this particular case right here, whenever we graph the data, what you'll notice is that, the graph will kind of look ugly. Theoretically, you can make a best fit line, but most of the line's not going to fit on there. Okay. For right now, what we're going to do is going to close out. And I hope that you guys all have a good day, and remember to stay lazy.